So forests is about 40 times 10 to the power of 6 square kilometers. The flux, 54, is the flux of water over the forests. And here you can see that there is indeed a measure of a unit measure. I said don't be concerned by unit measurements, but if you look at here, there is a unit measure. And these numbers are precisely given in terms of, you have to multiply each number by 1,000 cubic kilometers per year. So in this case, you have 54 thousandths of cubic kilometers per year. So again, 54 is over the forests, 0.3 is over the wetlands, 2.4 is over the lakes. I'm talking about rainfall and snow. 11.6 is over croplands. Croplands means cultivated areas for agriculture. 31 is over grassland. Grass is erba in Italian. 11.7 is over others. If you make the sum of this individual contribution, 11.7 plus 31 plus 11.6 plus 0.3 plus 54 plus 2.4, you get exactly 111. So you have an idea of the fluxes of precipitation over the different land uses. And then you have the precipitation over the ocean. You see it's more or less 4 times. If you compare this slide with the previous one, they are independent information, so you don't find the same numbers, but the order of magnitude is respected. And then you have evaporation from each land use. So this slide gives to you an idea of the water fluxes. In this case, don't misunderstand me, I will never ask you how much is more or less the amount of water that rains over the croplands. I'm not, you shouldn't focus on the fine details, but on the big picture. And the big picture is that the precipitation over oceans is 4 times precipitation over lands. The big picture could be that half of the precipitation is over forests. And you know, this is also gives to you gives rise to important consideration after the precipitation over the land over forests, which means that forests are indeed still occupying a wide portion of the earth. I think there is no one more. Okay, so basically with these few slides, I wanted to give you an idea of the total amount of water available and the water fluxes, just to get the big picture. Now, let's turn to what is our target? What's the target of humans, of society, when we get to deal with water? Of course, the first target is water security, which means providing water to people. This is the first target. But in order to provide water to people, you very often have to live close to water sources like rivers, like lakes, and this brings people exposed to water risks. This is strictly related to the need to secure water. If we had the possibility to live very far from rivers, it would be better because you are not exposed to floods. But indeed we have the necessity to go close to rivers for many reasons, not just for securing water. And of course, once that we get very close to water, we have the need to mitigate water risks. And the most relevant water risk is floods. Floods are usually not part of water resources management. I already mentioned to you that modern water resources management tends to include also flood management. We will stick on water security rather than flood management. I don't want to focus on flood management because, you know, this requires a very specific course, but it's very much important that we know that floods are an important problem for people. And this slide tells you some numbers. numbers that clearly say that floods are an important matter of concern. And you see here some numbers again. During the period 1991-95, the flood-related damage was more than 200 billion of US dollars. So it's representing close to 40% of all economic damage attributed to natural disasters. So it means that flood among the natural disasters are indeed one of the most important. Other natural disasters are earthquake, volcanic eruptions, etc. Floods is one of the most relevant. And therefore, this is the reason why there is a lot of research activity and a lot of efforts, even economical efforts, from society to mitigate the risk of flood. And then we have droughts, is another water risk, which is related to water security, to providing water for people. Water security means providing to secure water, so to provide water to people. And droughts are, a risk that is getting more and more important for some reasons that we will see now. First of all, you see that what do we see in these graphs? First of all, here you see the progress from 1990 to the last part is a projection to 2025 of the population in the southwest of the United States. And you see that it's increasing. Why it is relevant to focus on southwest? Because it's an arid area. In the past, people, of course, preferred to settle down in humid areas where a lot of water was available. And arid areas were left apart because it's, to live in arid areas is much more complicated, first of all, for securing water. But now, with the increase in global population, of course, people tend to live also in arid areas. So this is one of the reasons why drought are becoming more and more important. Because in the past, if a drought occurred in the southwest United States, nobody cared. Now, if a drought occurs there, we are forced to care. And this is an issue that you always have to keep in mind. People tend to focus on climate change and they tend to attribute any of the problem that we experience today with water to climate change. It's not just climate change. Climate change is, of course, relevant, but what is as much as important, I would say, at least as much as important, is population growth and the increased needs of water by people. In the past, people needed much less water than they need today, than what they need today. Because, with the increasing social level, with the increasing wellness of people, we tend to ask for more water. And this is the problem. There is global population growth, there is an increased water demand, individual water demand, and of course, it's not easy to provide water for everybody. And also there is climate change, and also there is water pollution. This is another problem, because in the past there was less pollution. This is a broad statement, but let us agree on this. In the past there was less pollution, and therefore there was more water available. And here, the second graph is what you see is the depth of water in two representative wells in the United States. You see a decrease of the groundwater level. A decrease of the groundwater level is not just concerning for the only reason that you may have saltwater intrusion. This is one reason of concern. But one may say that if you are very far from the sea and you are not concerned by salt water, you could exploit groundwater as much as you can. The problem is that if you have a decrease in groundwater, first of all, you need much more energy to get the groundwater to the ground surface, because you know, if the depth increases, you need more energy to extract the water, first of all. Second, you are not sure if whether or not this decrease is telling you that water is finishing. You may experience that after a while you decrease, and you get to the bottom of the aquifer, which means that water is not available anymore. And this is another reason of concern, because you know, groundwater takes some time to restore. If your rate of withdrawing, if your rate intensity of taking water is higher than the intensity of restoration, you get to a situation in which the groundwater is depleted, is finished. This is a history of recent drought in Europe. I make it short. The moral of the story is that in the last decades, in the last 3-4 decades, last 30-40 years, we noticed an increase in frequency of droughts in Europe. Some people say that this is just a perception, meaning that in the past we didn't perceive the droughts. Now we perceive them because we need more water. So some people say it's not climate change, it's just increased perception. Also, there is to say that the media communication now is higher and higher, it's more and more efficient than in the past. So it may be that now we have an increased perception of natural disaster because we get the news. In the past, people didn't get the news, and therefore they didn't have a so vivid perception. It could be, but there is also a significant probability that indeed the frequency of extremes is increased, just for climate variability. Climate variability or climate change, you can call it as you want. And for sure, climate is changing, for sure, even in the short term, for sure. And the big question is the attribution problem, as people call it, meaning climate is changing just for natural change, or it's changing because humans are impacting the climate. The question is relevant because the remedy is different. If you think that humans are impacting the climate, then you have to reduce the CO2 emissions, which is not bad in any case. But if you think that climate is changing because of its internal dynamics, then from this perspective, you shouldn't put a lot of economic efforts to reduce the CO2 emission, but you should rather put the money in mitigation efforts. Because, of course, if we accept that climate change is natural, then what we have to be concerned of is mitigation. Instead, if we accept the assumption that humans are impacting the climate through CO2 emissions, then we have to make an effort to reduce CO2 emissions. So the remedy is different. And given that money is limited, is not unlimited at all, money is limited, the attribution problem is important. So as I said, I make it short, but this is a story of the past drought in Europe. Let me just bring to your attention the drought of 2003 was indeed a drought that was very, very severe, with almost 3 months of no rain over a wide portion of Europe. Very severe. Water resources management, one of the missions is to learn how to manage these events. And this is just a map. You see, this is a map of Europe with some domains that were interested by the droughts. And the 2003 one, this big ellipses, covered most of Europe. Only the northern part of Swedish, Norwegia were not interested heavily. So what happens in the future then? There is one fact, and population is increasing. This is a fact. And it's an increase that probably will continue in the future unless something really unpredicted occurs. And I would say unless something of unpredicted unfortunately occurs. But if the conditions don't change significantly for natural disasters, for wars, for economic crisis, the population in the world is going to increase. And this is a projection of water scarcity in 2025, in 10 years from now, more or less. And this projection is developed by this agency. Of course, when we talk about projections, we have always to take into account that uncertainty is very relevant. But this projection says that by 2025, nearly 2 billion people will live in regions or countries with absolute water scarcity. And here they have printed in blue the countries that are not likely to experience problems. With the yellow, the countries with predicted economic water scarcity. Economic water scarcity means that water is potentially available, but people have no economic means to exploit it. And also they printed in red the countries with physical water scarcity, meaning that water is not available. And keep in mind that on average, over the earth, there is water for everybody. And there is enough water to sustain a significant additional growth of the total population. So on average, it's not a problem. The problem is that water is not homogeneously displaced in space and time. So you have some countries which don't have any problem, and you have countries which have very relevant problems. And to move water is not easy. You know that water is, has a considerable weight. It's not easy to move water. It's not easy even within a single country. And if you think about moving water from Alaska to Africa, of course you understand that it's not an easy issue. So this clearly justifies the need for studying water resources management, for devising efficient strategies for water resources management. There is an index that has been defined to quantify water scarcity. And this index is usually computed at the country level for each single country, and is based on an estimate of the renewable freshwater resources. The renewable freshwater resources are usually quantified by estimating the amount of fresh water that a country has at disposal every year. Renewable. Renewable means that this is a safe amount of water. If they use it, it doesn't compromise, the use doesn't compromise water availability in the future. So renewable means that it's renewed typically every year, because you know the seasonal cycle is 1 year long. So you get an estimate of the renewable freshwater resources, and then at the numerator you put the total water withdrawal minus desalination, because if you have some desalination, this is of course reducing the amount of water, the amount of fresh water that you use. So the minus sign is justified. And keep in mind that we don't have any concern about taking water from the ocean. You see how much water is in the oceans. So it's I don't remember, 97.5% of the total water. Fresh water is 2.5. So of course we are not really, at this stage, we are not concerned about desalination. So you get the total water withdrawal minus desalination, and at the numerator, at the denominator again, the freshwater resource is renewable, and if you get a percentage greater than 40%, which means that you are exploiting more than 40% of the renewable water resources, then we define this situation as a situation of water stress. And you can find on the web, for many countries in the world, a free database by the FAO, which is, I don't remember, sorry, the meaning of the acronym. It's Food Agricultural Organization, which is an agency of the United Nations. So there is a database that is called Aquastat. It's available on the web and gives for many countries in the world these numbers. Amount of renewable water resources, total water withdrawal, etc. And it's interesting to see that there are indeed a lot of countries for which the water scarcity index is assumes critical values. And you see a map, and you see that 0.4 is here, and you see that when it gets dark red, it means that the situation is critical, and the yellow is about 0.1, and therefore yellow and blue countries, white means no data, yellow and blue countries are in good conditions, and red and dark red countries are in critical situations. Now, how much water do we need? It's important to have an idea of how much water humans need. And let me introduce now an important concept. Because so far we focused on water availability. We focused on water availability and water scarcity. Now I'm turning into water demands. So I started my lecture today with water availability, and now I'm turning to water demands. And let me just clarify the concept, the theoretical setting. Every water resources management problem can be reconduced to a balance equation, meaning that you have to compare the amount of water that is at disposal with the water demand. This is the balance equation. Any water resources management problem need to be based on this balance equation. Water availability, water demands. So if you have to face a water resources management problem, you are called by a client who says, we don't have enough water, and so we don't know how to allocate the water that is available. Your first questions are estimate water availability and water demand, and apply a balance equation, which is very simple. I already mentioned to you, I think, that from a conceptual point of view, water resources management is very simple. They are the technical details which are difficult to estimate. Water resources availability is very difficult to estimate, even if the concept is very simple. The concept is just, I have to estimate how much water is available. But the technical way of doing that involves a lot of complications. And what is difficult, I said in my first lecture, is to communicate, to convince people, to have a relationship with the people. These are the problems. From a conceptual point of view, hydrology may be difficult. Water resources management, it's not very difficult. And the balance equation can be expressed in this way. Let's assume that you focus on a control volume, a volume in the space with respect to which you want to compute the water balance. And this control volume, I have some slides defining it later on. The control volume can be, for instance, a city, or can be a water supply system. So it's a region of the space, is a volume in the space with respect to which you want to compute the water balance. Or can be an artificial reservoir. The control volume could be the lake of an artificial reservoir. I want to compute the water balance. And then the water balance is very simply written. You can, if you indicate with W the amount of water, the volume of water that is stored in the control volume, in the reservoir, in the water supply system, in the city, and this amount of water which is stored in the control volume, of course, depends on time, the balance equation can be written in this way. The derivative with respect to time of the volume of water stored in the control volume can be written as the difference between the water flow that gets into the control volume minus the water flow that gets out from the control volume. This is a very simple mass balance equation. Again, QE is the water flow getting into the control volume, which means water flow means volume of water entering into the volume per unit time. QU is the outflow. And you see that the measure of unit is preserved, volume over time, and the flow is a volume over time. Every water resources management problem reduces to this very simple equation, which means that you have to estimate these two quantities. I have a city which I want to fill with water. I need to estimate the water entering into the city, for instance through a river from which people take water, and I have to estimate the water flowing out of the city, for instance because people open the tap to take a shower, so you need to estimate the human needs. When I say human needs, I include every need: civil, agricultural, industrial. Now let me make clear, I won't focus much during this course on water demands. I won't. I will not. I'm just giving an overview here, but I will not focus on water demands. I'm not focusing on water demands because usually water demands are estimated not by hydrologists but by hydraulic engineers. And usually in Italy, when we organize the academic career of our students in engineering, we deal in hydrology with the estimation of water resources availability, and water demands are taken care, are considered by the professor who teach hydraulic works and hydraulic design. So I won't focus much on this. I will focus more on estimation of water resources availability, which is a classical field of hydrology. But let me just give an idea. So how much water is needed by humans in general? Let's concentrate on the domestic water use. Let's start from here. And you see the amounts. If you have an high income country, typically we use from 100 to 600 liters per person day. This may seem like an exaggeration to you, like I don't really, you may think that you don't use so much water during the day. But if you think that, there is written in the next slide, a shower may take like 60, 70 liters of water, depending on how long you take the shower, then you realize that it's not so difficult to get to 100 liters. And I have this personal experience. I usually travel with the family with a camping car, and we have about 200 liters of water available in 3 people. If we really use only a few water, we last for 3 days, meaning that we need about 30 liters each, but it's really the minimum. The minimum. So if you go to low-income countries, you can go down to 10 to 40 liters per person per day, but this is really water scarcity. I challenge you to use only from 10 to 40 liters per day, including everything, washing, drinking, and etc. There are, of course, differences also. One important thing that you have to consider, this is the water that is actually used by people. This is the water that you use. the water that you have to take from the source is double this one, more or less, because you have losses, water losses during the transportation, during the water supply, along the water supply system. So this means that if you need 50 or let's say 100 liters per day for your personal use, this means that the aqueduct must take from the river or from the groundwater twice that to be safe. And this is why here you see that there are differences depending on the type of distribution. If the distribution is piped, or it's piped means that it's the water is carried to your home inside pipes, and instead the channels, for instance. If you use channels to convey waters, you have increased water losses because of infiltration, of course. But even if you use pipes, the most efficient aqueduct in Italy has an efficiency of about 80%, which means that the losses are about 20%. It's still relevant. It's still relevant. And this is an example of agriculture. Let's now shift to agriculture. And this gives an idea, this table, of the amount of water that is needed to produce a unit weight of selected quantities. And let's focus on the fact that 1 gallon is about 4 liters, it's 3.7, something like this. And 1 pound is, let's say, half a kilogram. So let's focus on here. 1 pound of cotton is less than half a kilogram, but let's focus on half a kilogram. Requires about 6,000 liters of water. This is really amazing. Yeah, 6,000. 1 pound of meat, beef, requires about 8 times 4, 3,000 liters of water, which means that when you eat like a Fiorentina steak, which is about half a kilogram, keep in mind that it requires like 3,000 liters of water to produce. But look at the proportion between the cotton and focus on the cotton. The cotton is a highly water requiring crop. 1 slice of bread requires like 500 liters of water, and 1 car, etc., and 1 kilowatt of electricity, and 1 10-minute shower requires about, let's say, 25 times 4. It's 100 liters of water. Now, let's note that the water requirements for agricultural production are indeed massive. Massive. And this allows me to introduce a concept. The major consumption of water is induced by agriculture, not civil use. And the proportion is about 3-4 times. And we will see some more details. So, let's say, let's give a more refined look at this issue. Domestic requirement requires from 100, we said, to 600 liters per person per day. So, which means from 40 to 240 cubic meters per person per year. Agricultural, industrial, and energy need, where agriculture is like 90% of this total, requires 800 cubic meters, 4 times. So, agricultural, industrial use, where agriculture, you could say just agriculture, is 4 times the civil use. So let's say that we need about this quantity of water per person per year, from 800 to 1,000 cubic meters per person per year, including irrigation, including everything. But again, irrigation is about 4 times civil use. And we will see the numbers for the Emilia-Romagna region. You will see a similar correspondence, 3-4 times. let's see what's the availability. Let me go back 1 second to this number, 1,000 cubic meter per person per year. This is the need to make a comfortable life. Now let's see the countries in the world, and there are some countries with no data, gray ones. For the other countries, let's say that yellow is corresponds to an availability of water which varies from 1,000, the amount that we identified for a comfortable life, to 5,000. So yellow, let's say that it's okay, but orange and red means water stress. And you see that there are some countries, even in Europe, where we have some water stress. In the current situation. Yeah, this is, sorry, I should have put this at the beginning, but it's just what I said. Now, let me focus on, just to finish the lecture of today, I want to mention to you an example, a very relevant and well-known example of a bad practice of water resources management. And you can find details on the Lake Aral disaster. If you Google Lake Aral, you get to a Wikipedia page which describes what happened there. The Lake Aral was a huge lake located in the former Soviet Union, very huge. And around the 60s, during the economical development, we call it the boom economico in Italian, the economical boom, the managers in the Soviet Union decided to make significant investments on the production of cotton. And cotton, you have seen that it's a